Once again, very good morning to all of you, dear students of the MSc Physics final class. We have been discussing the different methods of determining the crystal structures, in particular the X-ray diffraction techniques. Dear students, today I will introduce you with a new concept of reciprocal lattice. You are familiar that there is a real space and a momentum space. You are well familiar with these two spaces. They are reciprocal to each other. Whatever is localized in the real space is absolutely non-localized in the momentum space, and that which is localized in the momentum space is unlocalized in the real space. It means whatever accurate information by any technique we can obtain in real space can never be obtained in the momentum space, and vice versa. In the diffraction of X-rays, you see, I told you that there can be a condition that n1 lambda 1 equals to n2 lambda 2. It means corresponding to a particular, when we use monochromatic wave, then lambda becomes constant, and in that case n1 is proportional to d1 or sine theta. It means sometimes a single beam of X-ray that is monochromatic can produce simultaneous diffraction from different oriented planes of the crystal, and those diffraction patterns might be overlapping with each other, and we cannot get a proper information which we are seeking. So that's why I have written that when we consider the diffraction of X-rays from lattice planes of different orientations intercepting each other, then visualization is difficult, particularly in the real space. So we define inverse space of the real space, that is the reciprocal lattice space, and whatever information we are getting in the form of a plane in the real space becomes a point in the reciprocal space, lattice space. So I will explain it. It is easier to picture the collection of points in a space known as reciprocal space. So you must learn it, that whatever is a plane in real space converts into a point in the reciprocal lattice space. We know that a two-dimensional plane can be very well represented by its normal, which has only one dimensional representing the orientation of plane. This is what I want to explain once again for the students. In your earlier classes, you have been asked that whether a surface is a vector quantity or a normal or a scalar quantity. Dear students, we all know the law of parallelogram of addition of vectors. This is vector A, this is vector B, then the diagonal of a parallelogram represents vector R. But if I cross produce AB, that is A cross B, then I get the area of this parallelogram, because A cross B is AB sine theta n cap, and if this angle between A and B is theta, then this height, this is B, it will become B sine theta. So base into height is the area of the parallelogram, so I will get AB sine theta, the area, and n cap is the direction which is normal to the surface, plane of the surface. Using the right-handed screw rule, you can assign the direction n cap, and this is what I have written here, that We know that a two-dimensional plane can be very well represented by its normal, which has only one dimension representing the orientation of plane. So any plane can be simply shown by one direction that is normal to it, according to this very technique. Hence, if the length assigned to each normal is proportional to the reciprocal of the interplanar spacing of that plane, the points at the end of the normal drawn from a common origin in form of lattice is called the reciprocal lattice. This is the definition which you must remember and understand. We are following certain rules to construct the reciprocal lattice space. See, we assume first of all any lattice point as origin. From this origin we draw normals on parallel lattice planes. The length of these normals is taken as inverse of interplanar distances. The set of points on the tip of the normal is representing the lattice array. This is the way, these are the four steps which I shall take, and here it is. Let us calculate the reciprocal lattice vectors. In real space, we consider a primitive cell having the three axes A, B and C as shown. If we multiply the area of parallelogram formed by vectors B and C, see, B and C is the base and this is the vector A, and normal direction is D100. So if we multiply the area of the parallelogram formed by vector B and C with height of the parallelepiped or parallel three-dimensional primitive cell, then volume is area into the vertical, that is normal. So 1 upon D110 I will get as area upon volume. Area upon volume. Simple formula it is for you. If the unit vector normal to the region is n cap, as I have been telling you, B cross C will be BC sin theta n cap. So then this 1 upon D110 can be assigned a direction, and that is 1 upon D110 n cap is B cross C, area is B cross C upon the volume, and this is the reciprocal lattice vector of this particular cell normal to B cross C. Normal to the surface formed by B and C. B cross C itself is the direction. So the reciprocal lattice A star can be written as 1 upon D110, and it is denoted by sigma 100, and volume we all are familiar. Volume of any cuboidal cell is simply A dot B cross C. So it is B cross C upon A dot B cross C, the triple product, scalar triple product of the vectors. So similarly, if I consider area AB, then the direction will be along C. That will be the third vector, C star vector. Similarly, B star vector is the second vector of the reciprocal lattice space. So in this way, B star can be defined as n cap upon D010, C cross A. So B cross C, C cross A cross B. This is the cyclic symmetry in these particular vectors. So in this way, we come to the end of definition of the reciprocal lattice space vectors, and these equations represent the fundamental reciprocal lattice vectors. Thank you.